afternoon, everyone. We are glad to have you with us today and welcome to Stat Speaks, a colloquium on the statistical sciences, a forum where researchers may showcase and share their cutting-edge research. I am Adrian Glova, instructor at the UP School of Statistics, and I will be your moderator for today. So we have a compelling topic for today's colloquium. It lies in the intersection of non-parametric statistics, time series analysis, and even financial econometrics. And I'm sure that all of us will learn a thing or two this afternoon. But before we begin, allow me to share some reminders and the house rules for an orderly conduct of today's colloquium. So first, the audience are requested to reserve their questions for the Q&A forum at the end of each presentation. Second, the audience are enjoined to use the raise hand feature of Zoom to facilitate the Q&A forum in an orderly manner. Also, the audience may use the chat feature of Zoom to relay their questions, and audience members may send their questions to everyone or privately to the moderator for your questions. And of course, in asking your questions live or relaying it via the chat box, we request that you use the following format. So please state your name, your affiliation, whether that's your university, institution, or agency, before formally asking your question. So without further ado, I will introduce our speaker this session. Dr. Erniel Barrios is Professor 12 at the School of Statistics, UP Diliman, where he also served as Dean from 2008 to 2014. In 2010, he was awarded the Gawad Chancellor sa Natatanging Guro in recognition of his accomplishments and dedication to the university in teaching, research, and public service. His research interests span computational statistics, applications in spatio-temporal modeling, and big data analytics, resulting in over 80 papers published, mostly in statistics and computing journals. He has supervised the graduate research of over 140 students on various topics from computational stat to non-parametric methods, robust statistics, time series analysis, volatility models, and statistical machine learning techniques. He was elected member of the International Statistical Institute in 2012 and is a regular member of the Philippine American Academy of Science and Engineering since 2019. He is also a member of the International Association of Statistical Computing, the Econometric Society, the East Asian Economic Association, and the Philippine Statistical Association Incorporated. So ladies and gentlemen, let us all give a warm round of applause for our speaker, Dr. Erniel Barrios. Doc B, the virtual floor is yours.
Thank you very much, Adrian. Okay, good afternoon, everyone. Thank you very much for your time this afternoon. I actually started working on this paper in 2017 for a conference in Africa. And it took me, I waited until the pandemic to actually write the paper. And I asked the help of Paulo to work on the simulation study. And finally, last year, we were able to submit the paper for consideration in a journal. And we are now in the second revision of the paper. We also uploaded the paper in archive, so you can access this paper through archive. All right. Okay, so my original intention here is to synthesize the work of my students on multiple time series and volatility, and with the agriculture sector as the motivation, and then eventually for the focus of the paper, the journal where we submitted this focused on financial econometrics, so we have focus the motivation of the study. Okay, so I'm going to follow this outline. So I'm not going to read through. Okay, let me start with this framework of statistical inference in a traditional way. Um, Normally, we start by hypothesizing about the phenomenon of interest. We state null and alternative hypothesis. Then we collect the data. When we collect the data, we have to make it uh, this favorable for the kind of analysis that we're going to do. Say we want independence, identical distribution, because that would imply that we have homogeneous distribution. And then we also invoke the parent distribution to be normal, and or we draw large sample size so that the central limit theorem will hold. And then once we have the data, we summarize them into statistics. And then we have a sampling distribution, which we evaluate whether it supports the null or the alternative hypothesis, and then we make decisions. But in the process, we are looking at the validity or viability of the analytical distribution based on the data, so that we will be able to make decisions on which hypothesis to believe. And of course, the key is in the sample selection. We have to structure it in a way to facilitate the conduct of the steps that we have identified here. All right. On the other hand, what if we have big data as a data generating process? Many of the special features that I identified in the previous slide will no longer hold. For example, in telecommunications, you have usage data, and there are some revenue stream. There are end customers, there are key time points. We have independent customers, but they may be forced to behave similarly because of certain policies, like the credit limit, or possibly random shocks at the network level. So this kind of data that will be generated from this process will not necessarily be not necessarily fit to the one that we have described in traditional inference earlier. Also, we have the credit card data, where you have transactions, payments. The credit card holders are also independent, but because of the credit limit, minimum payment, and so on, they will be forced to behave in a similar way. And stock markets, for example, we have a high frequency here, and behavior of the stockbrokers and players in the market are usually influenced by news that can easily spread uh, across the market. And while they are related, the traders or the brokers are the same individuals or firms. Now, these dependencies are in fact time series data, and not just one time series, but several time series data can be generated. So some of this big data as a data generating process would necessarily lead to multiple time series. And contrary to the more popular multivariate time series, I'm going to compare the differences between multiple and multivariate time series in the next few slides. Okay, so um, Southern Oscillation Index is commonly used as an indicator of the extreme weather conditions. For example, very low negative, very high negative values of SOI is known to be associated with drought or El Nino or the El Nino episodes. And then two large positive values are typically associated with rainfall, and thus they are related with flooding. Now, some extreme events are noted here in this shaded areas. These are noted in the meteorology literature. For example, 1972 to 73, 82 to 83, this one, and then 1998 over here. These are typical confirmed El Nino years. And then 1999 over here is also a La Nina year. Now, what can this indicator cause in terms of agriculture in monsoon area, monsoon Asia, Southeast Asia specifically, which are dependent so much on rainfall? Now, yield is production per area. This is usually and usually in a destroyed plot because of extreme weather conditions. These are excluded in the computation of yield. Now, so I indicated here in these arrows times where there is a confirmed El Nino episode based on SOI, and so from here we would like to know what actually happened to yield of rice among Southeast Asian countries. So I think this covers all except Timor-Leste because I don't have sufficient data set for Timor-Leste. So, and excluding Singapore, of course, because they don't produce rice. So what happened to the yield of rice among Southeast Asian countries during those El Nino episodes? Are there any unusual patterns that we can observe here, or any stylized facts in the aftermath of weather extremes? All right. Here, for example, we are looking at standardized production, but these are not standardized over area as what we have in the previous slide for yield. Now, the behavior of production in the aftermath of this El Nino episodes over here seems to be prominent now. Here, for example, we can see for Malaysia, production has become exhibited more fluctuations, and then that's also true for other countries. Okay, now, on the other hand, let's now look at stock prices in Nikkei in Tokyo over here. So what happened during the Asian financial crisis? Ito yon. And then this one is the global financial crisis. So here, for example, it's not just declining, but you can also observe more fluctuations. Even here in this one, similar pattern can be observed. So it's not just declining stock prices. There's also severe fluctuation that you can observe. Now, this is in the Philippines uh, based on the PSEI opening prices. So ito rin yung Asian financial crisis, and this one is during the global financial crisis. So again, declines for and fluctuations can be observed during those periods. So this is the Hang Seng Index in Hong Kong. So you can also see here fluctuations and decline during the financial crisis. Okay, so from the time plots, we notice that there is a common process or factor underlying the movement of different time series. While each time series may be independent, a common process may drive their behavior to appear similar. Uh, 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 Sorry. My screen has, sorry about, sorry about that. Okay, I had problems with my screen. But anyway, so is my screen okay now? Okay, now, okay, sorry. So there is a common process or factor that drives each of these time series to appear similar. That's the latent characteristics. So that in rice production or yield, for example, weather can trigger the latency of the movements or the patterns exhibited in production or yield data. And then in stock market, spread of news or information can actually trigger the patterns in their movement. Now, so that with some latent factors common in this time series, uh, in rice production, for instance, we would like to know if there is volatility clustering. In stock prices, we would like to know if there is regional contagion, and we would like to treat the time series either in a multivariate versus a multiple time series. In a multivariate time series, we usually considers simultaneity among the time series. So there is latent characteristics that we are interested in to study specifically the structural dependence among the multivariate time series data. On the other hand, in multiple time series, we treat time series individually but potentially exhibiting some common patterns. Now, the patterns are typically driven by certain policies or events, and the result would manifest in terms of the common patterns that you can observe from each of these time series. Now, in multiple time series, uh, 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 the among the initial work related to this has been presented in 1977 by Bax and Chow, and they considered a canonical transformation of the autoregressive process. And then in 1996, Ackman and Gaugier considered a component extraction. So again, they are talking about latency among the multiple time series, so that this will help detect common sources of variation. And then the famous work of Arellano and Band in 1991 that defined dynamic panel models using general method of moments estimation to relax some orthogonality assumption for error and the excess. Now, while the Arellano band model has become very popular, there are some limitations in as far as the unbalanced data is concerned when the number of time series and the length of time series is unbalanced. In fact, uh, in cases where there are more time series than the length of time series, Arellano band estimator would not converge. So that in 2014 with my student here, we tried to uh, define a generalization of the panel data model by Arellano band, and we call this a multiple time series data, so that model rather. And we introduced here the um, uh, the time series specific random effect lambda I. So this part over here, that's just the usual dynamic panel model. We only introduced this one, and we estimated the model via the backfitting algorithm, and some examples that we used to motivate this problem are the portfolio of stocks, that each of the stocks have time series on it. And then two other students worked on clustering in multiple time series. So we modified the model in 2014. We added another uh, uh, factor, random effect here to account for clustering in time series. And then we illustrated certain characteristics, like clustering, for instance, can be caused by certain bank policies for credit card holders, or contagion in stock prices. And then the temporary structural change that we introduced in the work of Resi over here considers volatility spillovers and the effect of certain policies. Now, the models here, series of models actually, were estimated through the block bootstrap, which is based on the work of another student in 2011, where we embedded the forward search algorithm and the best linear unbiased predictor into the backfitting algorithm. So it's also a hybrid estimation procedure that aims to address uh, uh, structural change through estimation of the general features of the time series that is unaffected by structural change. So starting from this work, we tried to introduce robustness in terms of data search process, rather than on the characterization of the influence of certain observations. So we tried to induce robustness through the forward search algorithm. And uh, multiple time series and volatility was first introduced here in the work of Mark, where we also estimate this model in a robust way, taking into consideration presence of volatility. And of course, you have some of the volatility models that's available in the literature. Uh, there are many of them now, starting with the original work of Engel in 1982. That's the autoregressive conditionally heteroscedastic order 1 model, then generalized by Boleslav in 1986, and then the exponential generalized Garch introduced by Nelson in 1991. Okay, so with this in mind, now let's go back to the let's go back to the rice production data. This time, we considered not only Southeast Asia that is depending so much on weather conditions. So we now included 31 countries. They are taken individually. So here in the parametric test, we considered each of the 31 countries as in a separate time series. And then we considered we considered uh, the portmanteau test for lack of fit for the Q, and then the LM, that's the Lagrange multiplier approach based on the likelihood ratio test by Engel. So two parametric tests were applied on the individual time series for rice production, and we can observe that there's barely there's only a few p-values here that are less than 0.05, which means that the parametric test did not actually no, saw evidence on presence of volatility among this time series, and the 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 colored portion here represents this one. For example, these are the Central and West Asian countries, yung mga tans yung dulo. And then the second one, these are developed countries. This is the East Asia. This is Pacific Islands. And then itong malaking part, that's Southeast Asia. And then this one is South Asia. And you can see here the some of the those that have less than 0.1 p-values are these countries coming from the different regions. So you see that for Southeast Asia, only Myanmar manifested volatility among this time series. Now, we also have similar analysis, parametric test for volatility based on yield. So, mas lalong walang p-values less than 0.05 here. All right, and then if you look at stock prices, 7 of the 32 exhibits volatility. So for either or both portmanteau test for lack of fit, as well as the Lagrange multipliers, likelihood ratio test of Engel. All right. Okay, so you can see from here that if you treat the time series individually, there is low power. And by the way, our alternative hypothesis here is ARCH1. And the low power can be depending on the postulated model for volatility in the alternative. That's why I have to specify that we actually used ARCH1. Now, the question is, can we gain if clustered behavior is scrutinized instead of the individual time series? So here, we postulated clustered volatility in time series. So we have n time series data. Each time series have T observations, and then the model is given here. So the first component accounts for the dynamic behavior of the time series. And then lambda I is the uh, time series specific random effect. And then the error term here is, of course, a lambda I have this distribution. And then a UI is modeled in terms of volatility. All right. So that if sigma squared k kt here is significant, then that would indicate presence of conditional heteroskedasticity in cluster K. And we also assume that all time series within each cluster exhibit similar volatility model, and volatility models could possibly vary across the different clusters. And suppose that we consider Arch1, for instance, and then all NK time series in each cluster assumes similar parameters, and we need to estimate this. Furthermore, all time series share phi in the dynamic model with varying random effects, lambda I, for each time series. Okay, so we use these characteristics to study volatility or contagion across the regions. All right. So the the uh, the method that we are proposing here is a two-phase approach. In the first phase, we are estimating important parameters of the models, and then the second part is the testing part. So the the uh, the initial part of the estimation process is indicated here in this asterisk, and this is an iterative process. So we consider this as the BF iteration, and these steps would comprise one specific iteration. So of course, if this is the initialization phase step, we need to find some initial estimates. Otherwise, if you are already going through successive iteration, then the most recent estimates will be computed. So equation 1 from the previous slide will be the basis for the computation of the residuals. So we get an initial estimate of lambda I from best linear unbiased predictor, for example. The random effect can be estimated by the mean, and because expected value of lambda I is equal to mu I from our assumptions earlier. And then we compute new residuals. We subtract the initial estimate of the random component from YIT. So this is the first step in the backfitting algorithm. Okay, and then we estimate phi, the autoregressive parameter using bootstrap, and the substeps of the bootstrap are identified here. Okay, so I'm going to skip this one. The full details of this algorithm is available in our archive paper. So let me just run through the algorithm, the estimation algorithm that we proposed here. So then we computed new residuals which is a typical feature of the backfitting algorithm. You estimate a specific component and then get rid of the effect of this component from Y, and in the process, you are recomputing new residuals until the final residuals will no longer contain any information from pertaining to any of the terms included in your model. Of course, the backfitting algorithm is dependent on the additivity assumption of the model. That's very crucial. So that's what these steps are trying to do. And then here, we already estimate the volatility component also from the residuals after certain components has been estimated, and so on. So as I said, this is actually the backfitting algorithm, and the estimates are obtained sequentially. The idea is we would like to induce simplicity on the behavior of the models, so that estimation by component will be will facilitate the whole estimation process. Now, at this point, we have already estimates for each of the components. Then we iterate from the beginning, from the asterisk, starting with the random effects, compute new residuals, adjust the time series, and continue until convergence. So this time, we already have fully characterized equation 1. So may mga laman na lahat yan, including the variance components. After that, we will now proceed to the testing part. Okay. So how do we test for volatility? We first construct, after we have obtained the estimates from the previous phase, we will now reconstruct the variance components for each resample. So this is basically the sieve bootstrap that will allow us, since there's only one time series for each of the n time series, the goal of this part is to reconstruct different more than one time series for each of the n time series. So we do the sieve bootstrap to be able to do that. And basically, that's what this step here, generation of UIT star, coming from the normal with mean 0 and variance obtained from our estimate in the estimation phase. And then we compute the replicates following the model 1. And then we generated replicates for each time series data. And then this time series data, replicated time series data, are used in estimating the parameters again, so that we will be able to characterize the sampling distribution of each of the estimated parameters. So ayun, so the algorithm will derive the empirical distribution of the parameters in the model through a sieve bootstrap. Refer to Bullman 1997, for instance, for details of the sieve bootstrap. And then we use that in making decisions about the hypothesis that we are testing. So at this point, we consider now multiple clusters, and we are testing this simultaneously. And we auto-control the family-wise error rate or fewer following the Bonferroni correction. Of course, other techniques like Benjamin Hackberg can be considered. But in our case, since this will not be really large uh, set of hypotheses to be tested, we settled for the Bonferroni correction. And then we considered the bootstrap replicates from the seed, recreating the different time series so that you will have replicates. And then the estimates are computed, and then percentiles are constructed so that you can use that in deciding whether volatility is present or not, uh, following that volatility model that we have identified in Model 1. So these intervals comprises our basis on whether we have empirical evidence in favor or against volatility. Okay. All right. So let me go through. I'll skip that part. Okay. So we did a simulation study to initially characterize the behavior of the test procedure. So I'll just go straight to this one. So that is all. So what we can observe from this table is that in in general, the non-parametric test is correctly sized, as you can see from here, and exhibited a higher power over the parametric test. So the parametric test here is the Ingalls Lagrange multiplier test. And even when the time series are nearly non-stationary, for AR parameter is 0.95. Yan yung settings namin for nearly non-stationary. And lower power, of course, is expected as the time series approaches non-stationarity, because non-stationarity has masked the potential evidence for volatility. And that's true. That has been documented in many literature. Now, this one, we tried to to induce misclassification. For example, in this scenario, there should have been no volatility, but we introduced 2% of the time series with volatility, 10% with volatility, and so on. And for the different autoregressive parameters. And we can see that there is still relatively higher power, even with misclassified time series. Okay, then we illustrated this in stock market prices. And we are talking about contagion as well as volatility. Now, in 2018, this paper provided empirical evidence of contagion in the U.S. stock market to US, Japan, UK, France, and so on. So, all right. And then we considered 30 stocks, 19 from Europe, and then 11 from US. We considered daily prices from 2011 to 2016. And then we checked the literature for contagion reported within this region within the period. So ito yung European stock. So you can see that while they are not similar in terms of the fluctuations, you can see that there are episodes of severe fluctuations in certain stocks. Now, these are also for the US stocks, which is dominated by non-stationarity. And then we analyzed the original time series data individually, and some periods where volatility seems to exist were noted here. This can potentially be masked by overall non-stationarity, as I mentioned. And then Europe and US markets exhibit non-stationarity. In fact, the autoregressive parameters are 0.99 and so on. And then the parametric test for volatility failed to reject the null hypothesis of no volatility, which is given here. So you can see that the p-values are really small, except for this one, IXIC, which has a very small p-value. All right. So there is no evidence of volatility for the individual. And then we considered so original time series, ito yung non-stationary or near non-stationary. And then the non-parametric test computes this interval for Europe following borrowing information on the European cluster. The zero is not included here in the Bonferroni corrected confidence interval, which means that there is evidence of volatility as a cluster in the European market, which is not true in the US market because zero here is included. So from the simulation study, we know that power of the non-parametric test diminish when the time series are nearly non-stationary. Then we considered first differencing para maging stationary yung time series. And that's how the time plots look like. So here, even for the univariate analysis, we already saw more stocks in US and Europe to exhibit volatility. And then the more promising result here is in European and US markets. The Bonferroni corrected confidence intervals no longer includes zero, which means that for both clusters, for both markets, we were able to detect volatility, evidence of volatility or contagion, which is confirmed in the literature for these regions within this data period. And all right, so we verify the results here vis-a-vis the simulation studies, and they usually confirm each other's results. So parametric test for volatility identifies only one time series to exhibit volatility. The non-parametric test, though, provides empirical evidence that clustered volatility is present both in the Europe and US market. Okay, so concluding notes. Stock market indicators, meron tayong clustering of multiple time series, and then contagion is expected to complicate volatility, and the parametric test is typically characterized by incorrect size as well as low power. Test on volatility based on the bootstrap method can account for possible presence of contagion effect. And the test is fairly robust to distributional assumption. It depends on the nature of volatility. And then the test is correctly sized even in cases where the time series are almost non-stationary. And then powerful, especially when the time series are stationary in mean and that volatility are contained in only in fewer clusters. So what's the implication? This work offers a method of testing volatility in multiple time series that exhibit clustering, and that volatility spillover is contained only in few clusters. In contagion, whether this is local or global, The test can benefit from the simultaneous evidence that all time series can provide against absence of volatility. And then understanding of the presence of volatility will facilitate identification and estimation of models that can generate reliable forecast of indicators involved, hence better risk management in sectors that manifest such volatile behavior, like the financial markets. General abstraction of volatility clustering with multiple time exhibiting a generalized behavior can further enhance tools that can better understand features of some complicated phenomenon, including indicators in digital marketing or digital advertising, for instance. So that's all. Thank you very much for your time.
Thank you, Dr. Barrios, for that thought-provoking presentation. Personally, I found it interesting and useful to learn about clustered multiple time series. So it is a more nuanced analysis of time series compared to the univariate volatility models like GARCH or the multivariate treatment like vector autoregression. My understanding is we take into account contagion effects or the common underlying patterns exhibited by the time series. I'm sure that the other attendees also found the talk informative. And to further our learning experience, we are now opening our question and answer forum. Again, you may ask your questions directly to Dr. Barrios by raising your hand using the raise hand feature in Zoom. You may also ask your questions through the chat box by messaging me or everyone using the chat feature in Zoom. As a reminder, we encourage you to state your name and affiliation before formally asking your questions. So the virtual floor is now open to questions from the audience. But to get the ball rolling, here are some of my questions, sir. So I'm Adrian Glova, instructor at the UP School of Statistics. And my question, sir, is this study analyzes multiple time series. As you mentioned, sir, in the introduction, it is a different approach from the multivariate time series, such as vector autoregression. Can you clarify the difference again, sir? Because this is quite new to some of us.
Okay. So in multivariate time series, there is an inherent assumption of interdependence among your time series data, so that there is a specific assumption on the variance covariance matrix that is not diagonal, non-diagonal for this kind of time series data. In multiple time series, this is like the seemingly unrelated regression because the individual time series seems to be independent because, for example, wala namang kinalaman yung credit card holder 1 kay credit card holder number 2. However, because of the policies of the credit card company, they are pushed to behave similarly. And this is what we're trying to capture. Now, this will be simpler than the multivariate time series, and it will be more general than analyzing the time series in a univariate way. So the goal of a multiple time series is to simplify the complexity of the multivariate structure, but trying to account the specific features of the data generating process into a simultaneous analysis. So this is one of the models that has been triggered by the real-life data generating process from the presence of in the generation of big data, basically.
Thank you, sir, for clarifying the difference between multiple time series and multivariate time series. I guess as a follow-up, sir, since you weren't able to elaborate on the last portion. So, sir, the paper shows applications in financial markets We're interested, sir, if there are possible domains where this approach can be applied.
Okay. My main interest is really agriculture. Looking at the weather extremes, climate change, and the like. However, we focused on the financial market because we submitted this in an financial econometrics journal. So we have to tailor fit it to that area. However, I'm already trying to contemplate on using this in neuroimaging data. I got hold with neuroimaging data, and I already saw some, and in imaging data in general, RFID, RFeed, and so on, EEG, ECG, pwede rin siyang gamitin doon. I already started formulating some problems or some models related to those data.
Thank you, sir. So clearly, as what Doc P mentioned, the models are applicable to other domains as long as the multiple time series assumptions are satisfied.
Yes, the data generating process is there.
Yes. Again, we are opening the floor for questions, so please state your name and affiliation. So in the meantime, sir, I also found it interesting that the non-parametric test is better in terms of size and power compared to the Engels, Arch, Lagrange multiplier test, sir. Is there an intuitive or an intuitive explanation to this, sir? Why it performs better as far as size and power?
Okay. Parametric test is based on the asymptotic normality assumptions, actually. And then it is very specific to an arch model. Engel, for example, considers arch 1 as a model. So that if because of the stringent dependence on the distributional assumption, pag hindi AR1 ang totoong volatility model, hindi niya yan maka-capture doon sa test. Kaya yung power and size are generally affected. In our case, even if the volatility is not AR1, because we are generally capturing certain component of the volatility structure that where we construct the empirical distribution via the C bootstrap, mas nasusundan niya ngayon at kaya niyang i-characterize yung empirical distribution. Of course, this would still require more thorough mathematical exploration, and I'm going there hopefully very soon, not until the next pandemic.
Thank you very much, sir. So I guess that is the Q&A. And if other people have questions, you may send it to the moderator. And at this point, we cannot end the event without expressing gratitude and recognition to our speaker. So allow me to read and present to all of you our certificate of appreciation for Dr. Barrios. So the University of the Philippines School of Statistics awards this certificate of appreciation to Dr. Erniel B. Barrios in grateful recognition of his expertise and invaluable service as a speaker on non-parametric test for volatility in clustered multiple time series as a part of the UPSS Colloquium on the Statistical Sciences, given this 5th of May 2022 via Zoom. Signed, Dr. Imogen Evidente, Director for Research, UP School of Statistics, and Dr. Joseph Ryan Lansangan, Dean of the UP School of Statistics. Again, let's give a virtual round of applause and heart reacts to our speaker, Dr. Barrios.
Thank you very much. By the way, the paper is available in archive, so feel free to download if you want. And then if you have questions, just send me an email.
So we have come to the end of the program. Thank you to everyone who joined us in today's activity. We hope to see you attend, if not present, in our future colloquia and other events. Now, we would also appreciate hearing your thoughts and evaluation of our event. Kindly go to the link presented in this slide and answer the feedback form. The URL is also shown in the chat box for reference. Likewise, if you want to receive a certificate of participation, answer the same form in the given link and fill out the details accordingly. Please make sure to enter the correct information and the certificates will be emailed to you shortly. And if you wish to receive notifications on our future events, you may also subscribe to our mailing list at bit.ly/upstat mailing list. Again, that's bit.ly/upstat mailing list. Again, thank you everyone for attending and participating in this colloquium. We hope you enjoy the rest of the day. Thank you.
Okay, bye.